So I'm going to explain how you can actually implement the minimum compiler for the minimum subset of the C language for the assignment. So this is an overview of the spec that is clear in the definition of the syntax. So you can go into the syntax definition to make sure that this is the indeed the instruction that is imposed. So one important simplifications or restrictions are that all expressions have type long 8-byte integers. This is because there's no type defs. You can write you cannot write type def definitions in the top level, and you have no integers on floating point floats or doubles or pointers. So that simply there's no syntax to express these things. So all expressions having type long is a consequence of these syntactic restrictions. So everything is long. So type checks are actually not necessary, which is another huge simplification. And there's no global variable definitions. So in the top level of the program, you can only write a function definition. So the entire program is simply a list of function definitions. So you have to implement function calls following C conventions. So the functions your compiler generated can call or be called by C functions compiled by ordinary compilers. So you can go back and forth between machine code generated by your compiler and the machine code generated by other compilers such as GCC. So in terms of the statements, the only complex statements are if and while and compound statements. So for example, you have no for loops and you have no do while loops. And this is the structure of the program I have given to all of you. So I have explained them in another video. So I will briefly talk about this in this video. So the only thing you have to seriously look into is this MinC quotient. So you have to seriously look into other programs too, but this is the only file. Quotient is the only file you have to seriously modify. You have to seriously actually work on. So this MinC AST dot something has a definition of abstract syntax trees. So abstract syntax tree is a data structure that naturally represents the program. So it has a type definition to represent the whole program. It has a definition to represent a single function definition, a single statement, and single expression, and so on. So C means C, ST, dot, whatever for details. So let me show you what it looks like briefly. So in the case of, for example, OCaml, so you have this lib directory and you have mincast.ml. So for example, this is a type definition for type expressions, but to reflect the fact that you only have primitive long types. So the definition is as simple as this. This has a provision for introducing other primitive types other than long. So that this is the reason why it takes a string argument. But actually, the only type expression you ever have in the minimum subset of the C language is this type primitive long. And this is the definition of a variable declaration, which consists of type of the variable and the name of the variable. This is the definition of an expression, which may be literal constant integer expression like 1, 2, 3, variable whose name is given as a string. And this is some operator such as minus x or x minus 1, x plus y, x multiplied by y or something like that. And this is a function call expression. And this is an expression that simply encloses whatever expressions by parents. This is definition of a statement. It may be a empty statement, continue statement, break statement, a return statement that takes expression that specify the value that should be returned. And there's something called the statement expression that simply puts a semicolon after arbitrary expression like f of x. Compound statement consists of a list of declarations, variable declarations, like this, and the list of statements like this. And you have if statement and while statement. If statement consists of a condition and then and else clauses. Else clause is optional, so you have statement option. While statement consists of a expression that judges if the while statement should continue, like this, and the body statement. So it just keeps going all the way to the definition of the entire program, which is simply the list of top-level definitions. By the way, the top-level definition is only function definition. So something like that. So you have similar file for other languages, Go, Julia, and Rust, but I don't get into any of them. So like I said, most of your work will be conducted in this MINC cogen function, MINC cogen 5. So the top level function, whose name I don't remember, so it was something like AST2 instance program or something like that. So that function takes a path tree of the entire program and returns the machine code for it, so which is a list of instructions. So there's so many functions that takes one of these abstract syntax tree. So either for the entire program, for a single function definition or a single statement or a single expression, and returns the machine code corresponding to whatever abstract syntax tree is given to that function. So generating a machine code for a particular abstract syntax tree should be done in appropriate ways depending on what the abstract syntax tree represents. But generally speaking, it is done by generating machine code for its components and properly arranging them. So for example, at the top level there's a function that takes the whole program, the entire program, the abstract tree of the entire program. But generating machine code for the entire program it is basically done by generating machine code for each of function definitions contained in the program. So this is done by calling the appropriate code generator for function definition. And generating a machine code for a single function definition it is approximately generating the code for a statement, the statement, the body statement of the function definition. And generating machine code for statement should be done appropriately depending on the type of the statement. But you end up calling the same function on a component statement. For example, if statement has two sub-statements, so one is a then statement and the other is a else statement. So basically you end up with calling code generator for statement on each of these sub-statements. And at times you have to call code generator for expressions. So the point I'm trying to make is, so at first glance, generating the code for arbitrary C program looks quite complex and maybe daunting, but generally speaking, it simply has a lots of case analysis based on the type of the tree. So you do something different depending on the statement is while statement and if statement or compound statement. But otherwise, you simply use lots of recursive calls to child trees. So to illustrate this point, so let's consider how to compile the entire file. So how to generate the code for the entire program or file. So this is the given file, the file you are asked to compile, which consists of a list of function definitions. And if you remember how the C compiler generally compiles the entire file, you can easily imagine that this can be done by compiling each of these function definitions into separate assembly code sequences. And you may have to attach some boilerplate strings at the beginning and the end of the entire generated file. But the most essential work is simply delegated to whichever function that is supposed to take a single function definition and generate the code for a single function definition. So in OCaml, it will look like this. So definitions is a list of function definitions. You simply apply this function that takes a single definition and calls something like AST2 instance def, which is supposed to compile a single function definition. So you simply apply this function to all the function definitions by using something like map. And you simply concatenate all of them. So it is actually missing this prologue and the epilogue code you have to add to make it a complete assembly code that can be compiled by the GCC. But omitting these details, conceptually, it is as simple as this. So you simply call AST2 instance def on each of these definitions and concatenate the results together. So then you have to consider how to implement this AST2 instance def. So, but if you are given a single function definition, well, the essential work should be done by whichever function that takes a statement, the body statement in this case, and generate code for the statement. So the most, if not all, essential work is done by this recursive call into AST2 instance statement. So a function definition consists of function name, parameters, return type, and the body. And essential work, the most essential work is done by calling this AST2 instance for statement for the body statement. So you're going to have to add some boilerplate instructions, for example, to grow the stack space and save arguments if necessary. And at the end, you have to shrink the stack, and of course, you have to return to the caller. But these are fairly straightforward, and most complex work is simply done by this AST2 instance statement. So in this way, you can delegate the real work further into the code generator on its component, so the subtree of the given AST. So in this case, you delegate the work into the code generator for statement. So then let's consider how you would write AST2 instance statement, the code generator for a single statement. So as I said before, a statement has many possibilities. So it may be a if statement, it may be a while statement, it may be a expression statement. So let's take a while statement as an interesting example. So while statement consists of the condition expression that judges if the loop should continue, and the body statement that should be executed when the loop should continue. So again, the essential work should be done by these two subtrees. So you simply generate the code sequence appropriate for this conditional expression. And you should generate code for the body statement. You simply arrange them in an appropriate way. What I mean by the appropriate way is, so while statement should continue as long as this expression evaluates to true. So you put the code sequence that evaluates the value of this expression somewhere around here. And you put a label at the beginning of this instruction sequence. And you have the instructions corresponding to this body statement around here. And you first jump into the label and that evaluates the conditional expression. And after you evaluate the conditional expression, you compare this the value with 0. And if the value is not 0, you should continue the loop. So you should jump into the label that indicates the beginning of the body. So you simply arrange the generated code like this. So in terms of the program, it first calls something called the AST2 instance expression. So the code generator for an expression on the condition statement here. and you get an instruction sequence for the body statement by calling the same function AST2 instance statement. The same statement, the same function you are exactly implementing. And you arrange the generated code in this way. So at the beginning, you have a jump instruction to the beginning of this condition expression. And after the condition expression, you do these things. And you have instruction sequence for body somewhere between LS and LC. So you keep doing something like this until you define everything you need to define. So what is left undefined yet is this AST2 instance expression. So let's consider how you can do that. So take as an example how you compile ordinary arithmetic expression like something plus something. So again, the principle is the same. So you simply call AST instance, so AST2 instance expression on each of these operand expressions. And you arrange them in a particular way. So in this case, you first evaluate the second operand. And after you get the result of the second operand, you put the result into somewhere so that it is not destroyed during the execution, the evaluation of the first expression. So you then go on to evaluating the first expression. And then because this is an addition expression, you add these two results together. So just recall that we are following the simplest strategy of saving all intermediate results on the stack. So we are not trying to optimize things in any way by trying to keep the results of this expression on the register while you are evaluating the first expression. So essentially the same, but slightly different in detail is how you can do the similar thing for comparison expression, like A smaller than B. So this is somewhat different, primarily because there's no direct expression. There's no direct assembly instruction that does this exactly. So recall that what A smaller than B should be evaluated to in the C language. So A smaller than B is an C expression that evaluates to 1 if this condition holds, 0 if this condition does not hold. So like I said, there's no single instruction that exactly does this. And one thing that you have to know is that this expression, so this is an expression. So this expression can appear anywhere other types of expressions can. So for example, so it typically appears in the condition part of the while or if statement. But the point here is that generally speaking, it is not the case. For example, you can have an assignment expression like z equal x smaller than y. So it assigns either 0 or 1 depending on whether this condition holds or not. So you can even write something like x smaller than y plus z. So it evaluates to either z or 1 plus z depending on x is indeed smaller than y or not. Or f of x smaller than 1. So it ends up with calling f with argument 0 or 1 depending on x is smaller than 1 or not. So you have to consider how to do this in the assembly code. So one way you can do is to use a conditional branch. So you first compare A and B, and depending on the result, you execute a different execution, different instructions. So in one branch, you set the result to 0, and in the other branch, you set the result to 1. But it is not terribly efficient. So there's actually a better way, something called conditional set instructions. So for example, you compare these two things, RDI and RSI, and then you issue another instruction, one of the conditional set instructions. So in this case, an instruction is called set LE. So it sets this register to 1 if the last comparison is less than or equal to 0. So it is essentially comparing RDI and RSI. And if RSI minus RDI is less than or equal to 0, then it sets this register to 1. So in this way, you can obtain the desired results. So by first setting the destination register to 0 and execute the comparison, and if the condition is met, you assign 1 to the same destination register. But by the way, this AA register is the last 8 bits of this RX register. So you are essentially assigning the value to the same register. So with that in mind, this is how you can compile a comparison expression. So like before, you call the same ST2 instance expression on each of these operands, and you arrange these code sequences, generated code sequences in this way. So after you get the first, you get the result of the second operand, you save it somewhere, and here you get the result of the first operand. So you first set the destination register RX to 0 and compare these two values. So you first need to move one of these operands to register, and you compare this register with the other argument, and you set the register RX to 1 if this condition is met. Set L. So set if less than 0. So this is how you can compile a function called expression. So the conceptually again, it is very similar. So you simply call IST to instance for expression for each of these arguments. So the only difference is that you may have an arbitrary number of sub-expressions. But conceptually, it's very similar. So you simply arrange code sequences generated by each of these arguments, and each time you put the results into somewhere in the stack. And after you evaluate all these arguments, you put these arguments into places designated by the ABI, Application Binary Interface, or calling conventions. And after you put arguments into appropriate places, you finally issue a call instruction to jump into the specified function. So, but by the way, sorry, it should be call F, not call Q, to call function F. So actually, that's pretty much it. But there are some important details I have not talked about, so I have left out. for the purpose of simplifying the explanation, which is how to determine locations to save values of sub-expressions and variables. So I have explained, for example, how to compile a plus b in this way. So after you obtain the, for example, one of these results of the sub-expressions, you put the result into somewhere in the stack without talking about where it is exactly and how to determine this offset exactly. So this should be done in such a way that during the evaluation of the other argument, this place shouldn't be destroyed. So evaluation of this argument is going to use somewhere in the stack too, right? But this piece of code shouldn't use this location. So this is what you have to maintain. So to that end, AST to instance expression, the code generator for an expression should receive a value, let's call it a V, pointing to the lowest end of the free space. So it takes another variable V in addition to the AST of the expression you have to compile. And this value, an integer value, specifies the lowest end of the free space, which means that this function call should generate instructions that evaluate E using or equivalently destroying only addresses above RSP plus V. So this is the convention with which we can guarantee that necessary values are not destroyed. So to be more specific, it takes V when you are asked to compile this expression. And when you evaluate one of these sub-expressions, it again passes the same value of V. And it then moves the obtain the result into RSP plus V. And when you generate the code sequences for evaluating the first expression and this one, it says you should use addresses only, it should use only addresses above V plus 8 to make sure that this location is not going to be used by the code sequence that evaluates this expression. So this way you can guarantee that necessary values are preserved. So a similar consideration must happen for determining the locations for variables, not intermediate results for evaluating expressions. So for example, in this compound statement, you need to hold A, B, and C on the stack during the execution of this compound statement, right? And whether the problem is almost identical to saving values of sub-expressions I have just talked about. So to that end, AST2 instance statement, the code generator for a statement, also takes V pointing to the beginning of the free space, the lowest end of the free space. So the AST2 instance statement given S and V should generate instructions to execute S, only using or destroying addresses above RSP plus V. So given this specification or convention, you can determine that A should be held in RSP plus V, B should be held in RSP plus V plus 8, C in RSP plus V plus 16, for example. So in a way, very similar to how you can preserve the result of sub-expressions. But one thing that is slightly different between saving the result or preserving the result of sub-expressions and saving the result, saving the value in the variable, is that a variable may occur in any expression in the scope. So unlike sub-expressions, you cannot know where it might be used elsewhere in the program, right? So for example, when you have a variable x, there might be an expression x plus y, x plus 1 in pretty much anywhere in the compound statement that defines this variable x, right? So in order to compile x plus 1, you obviously need to know where x is held. So you have to make a data structure that holds a mapping between variable and its location. And it is generally called an environment. So you have to pass it to AST2 instance statement and AST2 instance expression. Because if you are given an expression, that expression might contain x or other variables within the scope, right? And to compile such a expression, you need to be able to know the location that holds the value of whichever variable you are referencing. And when new variables are declared or introduced at the beginning of a compound statement, you have to add new mappings to it. So with that in mind, this is what AST2 instance expression, the code generator for expression, eventually will look like. So it takes an AST of an expression, an environment, and V, the lowest end of the free space in the stack. And for example, when you are asked to compile X, a variable, then it should look up the environment to know its location. And it extract the value of X from that location, presumably using some sort of move instructions. So here env lookup xm asserts the environment m for x and returns its location. And AST2 instance statement also should receive an environment too. And when you compile compound statement, you take the declarations and you have to extend the environment using declared variables. So here env extend, that takes a list of declarations, environment, and the lowest end of the free space in the stack. It assigns locations v to the first variable declared, v plus 8 to the second variable declared, v plus 16 to the third variable declared, and so on. Register them into this environment. So extend the environment to reflect these assignments. And return the new environment m prime and the new free space v prime, so that subsequent statements are going to use only spaces above RSP plus v prime, for example. So you can implement this environment data structure by a list of variable name and locations. So for example, env lookup xenv is simply looks for an tuple whose first element matches this variable name that is searched for, and returns whichever location that is paired with the corresponding variable. Env add is an function that adds a single pair of variable name and location to this environment. So it simply adds a new pair x lock at the beginning of this list. And of course, extend env can be implemented by repeatedly calling this env add. The env extend is the one I have just talked about in the last slide. So with that, you can hopefully have a fairly clear idea about how you can implement a compiler for the minimum subset of the C language. So I hope you enjoyed the work and finish it.